In the Amazon, not every silence belongs to teeth. There are mornings when the forest does not tighten because a predator has entered, but because the air itself has shifted. The change begins invisibly, high above the canopy, where rising columns of warm, moisture-heavy air meet cooler descending layers at the edge of a forming storm. Barometric pressure dips almost imperceptibly. Humidity thickens before the first drop falls. Wind currents reorganize. Light becomes slightly metallic, diffused through swelling cloud banks. Long before thunder travels across the basin, the forest recalculates. On the leaf litter below, a poison dart frog that had been calling steadily from the base of a bromeliad stops mid-note. These frogs are small, often no larger than a human thumb, yet they are among the most chemically defended vertebrates in the Amazon. Their skin carries alkaloid toxins derived from specialized diets, primarily ants, mites, and other arthropods, whose own chemical compounds are sequestered and repurposed. The brilliance of their coloration, electric blues, molten oranges, lacquered yellows, advertises that defense in daylight. They are diurnal, bold in appearance, and unusually conspicuous for amphibians. Their survival does not depend on camouflage, but on chemical credibility. Yet their vocalization is far more sensitive than their color. Male poison dart frogs call to establish territory and attract mates, producing high, rapid pulses that cut through understory noise. These calls are not random. They are tightly linked to hydration, temperature, and atmospheric stability. Amphibian skin is permeable, designed for gas exchange and moisture absorption. That permeability makes them exquisitely vulnerable to desiccation and pressure changes. Even slight shifts in humidity can alter metabolic rates and water balance. When barometric pressure drops ahead of a storm front, amphibians detect it. Research suggests that many frog species adjust calling behavior in response to falling pressure, often reducing or halting vocalization. The mechanism is partly physiological and partly behavioral. Lower pressure can precede heavy rainfall, and rainfall dramatically alters acoustic transmission. Raindrops disrupt surface tension, drown out mating calls, and physically interfere with sound propagation. Calling during these moments wastes energy and reduces signal clarity. Silence becomes efficiency. At ground level, the effect is subtle but cascading. Insects, particularly flying species, also respond to pressure shifts. Many reduce flight activity before storms, descending into shelter as air density and turbulence change. Stridulating insects may slow or stop. Birds, sensitive to wind pattern changes and shifting thermal currents, adjust foraging routes or return to more stable perches. The understory loses layers of incidental noise, not because of predation, but because physics has altered the medium in which sound travels. The jungle appears to power down. A frog that had been calling rhythmically from a low leaf falls quiet. A neighboring male does the same. Within minutes, the acoustic patchwork dissolves into pockets of stillness. The canopy may remain active in isolated bursts, but the ground-level chorus fades. It is not fear, it is atmospheric recalibration. Poison dart frogs are particularly sensitive to microclimate because reproduction depends on precise moisture conditions. Many species lay eggs on damp leaf surfaces, often under protective cover. Males guard clutches, hydrating them with their own bodies, or transporting hatched tadpoles on their backs to small water pools in bromeliads or tree holes. These tiny phytotelmata, water-filled plant cavities, must retain sufficient volume to support larval development. Storm intensity, evaporation rate, and humidity gradients all affect reproductive success. Calling at the wrong time risks energy loss when breeding windows are closing or conditions are unstable. Their metabolic strategy reflects this precision. Unlike large mammals that can buffer internal changes, small ectothermic amphibians experience environmental fluctuations directly. Skin moisture, ambient temperature, and oxygen diffusion through damp substrates all influence activity levels. A drop in pressure signals incoming instability, and behavioral restraint conserves both water and energy. From a human perspective, the silence can feel ominous. You may have learned that sudden quiet means predator presence. Earlier, a hush in the canopy suggested strategic concealment. At the river's edge, calm water meant ambush geometry. Here, however, the quiet is meteorological. The forest is not bracing for attack. It is adjusting to atmospheric mechanics. If you misinterpret that quiet as predation risk, you may rush. Anxiety accelerates movement. You step faster across slick leaf litter, scanning for unseen eyes instead of watching your footing. Moisture has already increased on surfaces. The first fine mist preceding rainfall lubricates bark and roots. A misstep on a mossed trunk can send you sideways into shallow ravines. In your urgency to escape imagined teeth, you generate real noise. That noise travels. Large predators respond less to atmospheric quiet than to disturbance. A fall, a sharp exhalation, gear clattering against wood. These are anomalies in a dampened acoustic field. The irony is structural. Panic at a physics-driven silence can produce the very signals that draw biological attention. Meanwhile, the poison dart frog remains motionless beneath a leaf, its bright body pressed against moist substrate. Its aposematic coloration is irrelevant in that moment. It is not advertising, it is conserving. The toxins in its skin, batrachotoxins in some lineages, pumiliotoxins in others, are metabolically expensive compounds derived from dietary specialization. Without consistent access to specific arthropods, captive individuals often lose toxicity over time. Their chemical defense is therefore tightly linked to ecological stability. Storms alter insect availability. Silence during pressure drops may also reflect anticipation of dietary disruption. Bird predators such as motmots or jacamars occasionally prey on dart frogs despite toxicity, often targeting species with lower alkaloid concentrations. Some snakes exhibit partial resistance to certain toxins. The frog's warning colors function best when visibility is clear. Heavy rain reduces contrast and complicates visual detection. Calling in such conditions would draw attention without enhancing mating success. Again, silence is strategy. As the storm edge approaches fully, the forest's behavior changes again. Wind arrives in uneven pulses, shaking canopy layers and sending debris downward. The first large drops strike broad leaves, creating percussive impacts that overwhelm smaller acoustic signals. At this point, even if frogs resumed calling, they would be acoustically erased. The earlier hush was preemptive. Then the rain commits. Water cascades through vertical space, saturating bark and filling ground depressions. Bromeliads brim. Temporary streams form along root systems. For poison dart frogs, this is both risk and opportunity. Increased moisture expands safe movement zones. Dehydration risk decreases. Tadpole transport becomes easier. Yet flooding can wash away eggs or alter microhabitats. Once the storm stabilizes and pressure equalizes, sound begins to return. Insects resume flight cautiously. Birds test brief calls between rain intervals, and from beneath a low leaf, a single dart frog restarts its high-pitched pulse. The acoustic economy rebuilds from fragments. The microclimate switch reveals a deeper principle of rainforest ecology. Not all silence signals predation. Some silence signals atmospheric negotiation. Organisms finely tuned to humidity and pressure adjust before humans perceive change. Their restraint is not fear-driven, but physics-driven. Understanding this distinction matters. If you learn to differentiate predator-induced hush from meteorological hush, you move through the forest with clearer judgment. Predator silence often carries tension, abrupt, localized, layered with vigilant posture. Storm silence spreads more gradually, accompanied by thickening air and subtle wind shifts. One is behavioral compression. The other is environmental recalibration. Poison dart frogs, small as they are, function as barometers with legs. Their calling patterns map microclimate transitions in real time. They are not merely colorful ornaments of the understory. They are acoustic instruments responding to pressure gradients invisible to human skin. In the end, the jungle's power down before a storm is not emptiness. It is transition. The forest conserves energy, reduces broadcast, and prepares for impact. If you misread that physics as threat and rush blindly, you create new variables in a system already adjusting. The frogs did not go quiet because something is hunting. They went quiet because the sky is moving. And if you pause long enough to feel that shift in the air rather than outrun it, you begin to understand that survival in the Amazon is not only about spotting predators. It is about reading atmosphere. Before a jaguar is ever seen, the forest begins to reorganize around it. The Amazon does not fall silent in a dramatic sweep. Instead, it tightens. Sound does not disappear. It thins, compresses, and becomes selective. A moment earlier, the understory carried a textured rhythm. Ground doves shifting through leaf litter, small passerines stitching short flights between branches, insects maintaining a steady metallic pulse from hidden perches. Then the repetitions begin to break. A call ends half a note early. A hop pauses mid-pattern. A foraging scrape stops without completion. Nothing looks catastrophic, but the structure of the soundscape has changed. This shift happens because jaguars move as pressure, not spectacle. Their anatomy supports this strategy. Thick digital pads cushion each step, distributing weight across damp soil and brittle debris. The limbs are built for compression and release, dense muscle anchored to a flexible spine that can coil and explode within a single stride. Unlike endurance predators that chase prey across open terrain, jaguars hunt through geometry. They close distance quietly, align angles, and commit only when probability favors a decisive outcome. The forest responds not to noise, but to proximity. Prey species do not wait for visual confirmation. They survive by detecting irregularity. In the Amazon, patterns are everything. Birds hop with rhythm. Rodents chew in bursts. Even insects stridulate with measurable intervals. When a large predator enters an area, those patterns destabilize in ways that ripple outward. A ground-foraging tinamou raises its head slightly higher than usual. An agouti freezes with food suspended between incisors. A mixed species bird flock reduces chatter and increases vertical spacing between individuals. None of these reactions are dramatic alone, but collectively they generate a behavioral contraction. Microcues drive this contraction. A fresh scuff in leaf litter exposes darker soil beneath oxidized layers, signaling recent mass displacement. A snapped twig bent laterally instead of downward suggests horizontal force. Even subtle scent drift plays a role. In humid rainforest air, chemical traces cling close to the substrate. Mammals sample these gradients constantly, passing volatility changes invisible to humans. The jaguar's presence alters airflow chemistry, and prey detect it long before human senses register anything unusual. The forest operates as a distributed sensor network. Animals monitor one another as much as they monitor predators. If one bird interrupts its repetitive call, neighbors adjust. If small mammals reduce movement, the reduction itself becomes information. The result is not panic, but restraint. The Amazon does not empty, it concentrates. Energy that was allocated to feeding or display is redirected toward vigilance. Thermal dynamics influence this interaction as well. Jaguars often exploit cooler crepuscular periods when heat stress is reduced. In a humid ecosystem where evaporative cooling is inefficient, conserving thermal energy is critical. Remaining motionless in dense understory requires metabolic discipline. Explosive movement must be brief and efficient. Prey species also operate within these temperature windows, balancing feeding necessity against predation risk. The overlap compresses vulnerability into narrow slices of time, making early detection vital. As this recalibration spreads, the acoustic environment shifts. Insects reduce their steady pulse. Birds shorten their phrases. Small mammals limit leaf disturbance. In a forest where background noise has thinned, any consistent sound becomes amplified by contrast. This is where a human presence becomes conspicuous. Human locomotion is rhythmic. Heel strike, weight transfer, toe push-off, repeated with mechanical consistency. Most rainforest animals move irregularly. Advance, pause, listen, adjust. Irregularity minimizes detectability, but a steady gait creates a predictable acoustic signature. In a compressed soundscape, predictability stands out. To a jaguar, tuned to low-frequency substrate vibrations and subtle leaf displacement, rhythm is easy to track. Trails amplify this effect. Cleared or repeatedly used pathways reduce vegetative density, simplifying approach angles. Wind moves more cleanly along linear corridors, carrying scent in defined channels. For an ambush predator that prefers minimal energy expenditure, such geometry is advantageous. The jaguar does not need prolonged pursuit. It needs a moment where distance collapses efficiently. Linear movement along a predictable route simplifies that calculation. Visually, the predator remains almost invisible. The jaguar's rosette pattern fragments its outline in dappled light. Instead of presenting a solid mass, the coat breaks into irregular shapes that mirror sunlit gaps on the forest floor. Even melanistic individuals retain faint rosettes, visible at certain angles, preserving camouflage under low light. The predator does not need to disappear entirely. It needs only to delay recognition long enough to close space. Meanwhile, prey tighten further. Peccaries bunch closer together, their bristled dorsal hair lifting subtly in alert posture. Arboreal primates shift to branches less accessible from below, increasing vertical separation. Ground birds hold still rather than flushing. Sudden flight can draw attention. These adjustments reshape the forest's energy flow. Feeding slows. Movement corridors shift. The landscape of fear updates in real time. This landscape has evolutionary consequences. Chronic predator presence alters where prey feed, how long they forage, and which habitats they avoid. Reduced feeding time can affect body condition and reproductive output. Over generations, these pressures shape morphology and behavior. Heightened sensory acuity, faster response thresholds, flexible habitat use. The jaguar's influence extends beyond individual hunts. It structures ecosystem balance. From a mechanical perspective, the jaguar's lethality reinforces this pressure field. Unlike many big cats that suffocate prey, jaguars frequently deliver a crushing bite to the skull or cervical spine. Their jaw strength relative to body size is exceptional among felids, allowing penetration of bone in species like capybaras and caimans. This efficiency reduces prolonged struggle and secondary noise. For prey, survival depends less on outrunning a chase and more on detecting presence before commitment. If you continue walking unaware, you become the only consistent rhythm left. Every footfall transmits through compressed leaf litter. Every gear shift or fabric brush carries farther in a dampened soundscape. The forest has reduced its casual broadcast. Your movement now dominates. The jaguar may observe briefly, assessing size, posture, scent. Most encounters end without escalation. Jaguars rarely target humans under normal ecological conditions. Energy conservation governs decision-making. Yet the lesson is not about attack frequency. It is about perception. The most critical phase of a predator encounter often occurs before contact, during the behavioral contraction that precedes visibility. Silence, in this context, is not absence. It is concentration. The ecosystem has detected and adjusted before your awareness engages. Standing within this recalibrated forest, you begin to understand that the first signal of danger is not movement toward you, but movement away from normal. Repetition shortens. Casual motion stops. Patterns thin. The jaguar may never reveal itself, but its influence is measurable in altered rhythms and compressed sound. The pressure field exists independent of spectacle. It is built from micro-cues, sensory networks, and evolutionary memory. By the time you sense that something feels different, the forest has already completed its adjustment. The predator does not need to announce itself. The ecosystem does that first. And if you learn to read that shift, the subtraction before the sighting, you are no longer walking blind through a living equation. You are reading it as it updates around you. Before sunrise in the Amazon, the canopy usually announces ownership long before light reaches the forest floor. Low, resonant roars roll across the treetops, overlapping from ridge to ridge like distant thunder that never quite breaks into storm. These calls belong to howler monkeys, among the loudest terrestrial mammals on Earth relative to body size. Their voices can travel several kilometers through humid air, threading between emergent trees and echoing along river corridors. At first impression, they seem to define the jungle's acoustic identity. Yet their true power lies not only in how loudly they broadcast, but in when they choose not to. Howlers are regulators of sound economy. Their calls are not constant displays of aggression, but calculated investments in territory maintenance. Enlarged hyoid bones in the throat act as resonating chambers, amplifying sound without requiring extreme muscular exertion. This anatomical adaptation allows them to project dominance across vast canopy spaces while conserving energy. By roaring at dawn and dusk, they advertise occupancy, reducing the likelihood of direct physical confrontation with neighboring troops. Sound replaces combat. Territory is negotiated acoustically. But there are moments when that negotiation stops. A troop that has been roaring consistently may fall abruptly silent. Leaves still rustle as individuals reposition along branches, but the deep, guttural chorus vanishes. This silence is not absence, it is restraint. In predator-rich environments, broadcasting location carries cost. Jaguars occasionally climb low branches, and harpy eagles patrol upper layers with predatory precision. A sustained, repetitive roar provides spatial coordinates to any listener. When risk elevates, silence becomes adaptive. The decision to stop vocalizing is rarely isolated. Howler monkeys live in social groups that rely on coordinated vigilance. If one individual stiffens posture and reduces movement, others register the change. Postural cues ripple outward. Tails curl tighter around branches. Juveniles draw closer to central trunks. The troop's acoustic output declines not from panic, but from collective calculation. Sound, in this context, is currency. It is spent to maintain boundaries and withheld to avoid detection. Speculation grounded in canopy ecology suggests that one troop's silence can trigger broader cascades. Sound travels efficiently across upper forest layers. When a neighboring group fails to respond to routine dawn calls, that absence is itself information. If territory usually marked by reciprocal roars remains quiet, nearby groups may adopt similar restraint. The result is a canopy-level hush that spreads across contiguous territories. The forest floor may still carry insect noise and distant bird calls, but the dominant bass register disappears. The jungle feels hollowed from above. This is not fear in the cinematic sense. It is strategy embedded in social behavior. Howlers occupy an unusual ecological niche. They are primarily folivores, consuming large quantities of leaves that provide limited caloric density. Digesting this fibrous diet requires specialized gut microbiota and prolonged fermentation in an enlarged hindgut. Energy budgets are tight. They conserve movement, resting for long intervals to offset low nutrient intake. Vocal displays are metabolically cheaper than physical disputes, but still carry energetic cost. Silence conserves both calories and safety. Their sensory world reinforces this economy. Vision in the canopy is fragmented by overlapping foliage. Auditory cues bridge those gaps. Howlers track neighboring troops by listening rather than seeing. When a familiar acoustic map shifts, the absence stands out sharply. In this sense, silence can be louder than noise. It signals that normal territorial exchanges have been suspended. Predator interactions further shape this behavior. Harpy eagles, apex aerial predators, are capable of striking monkeys from above with devastating efficiency. Their approach is often silent until the final wing beat. Jaguars, though primarily terrestrial, are competent climbers capable of ascending trunks to surprising heights. In both cases, predictability increases vulnerability. A troop broadcasting its location repeatedly provides a fixed point in three-dimensional space. Silence disrupts that targeting. From below, a human moving through the understory may misinterpret this hush as emptiness. Without the rolling resonance of howlers, the canopy feels vacant. You push forward, believing the upper layers are inactive. Yet above you, dozens of eyes track movement without sound. Howlers possess trichromatic vision in some species, allowing detection of subtle color variations in foliage. They monitor changes in canopy texture and movement. Your passage is visible as displaced leaves and shifting branches, even if no call acknowledges it. The canopy functions as a surveillance network. Other primates, birds, and arboreal mammals observe and respond to each other's cues. If howlers reduce vocalization, neighboring species often decrease conspicuous movement. Alarm calls in many primates are context-specific, differentiating aerial from terrestrial threats. But withholding calls can be equally strategic when revealing position outweighs warning value. The balance between alerting allies and avoiding predators defines the alarm economy. Thermoregulation also influences vocal patterns. Dawn and dusk, when temperatures are lower, favor sustained roaring. Midday heat often suppresses activity. During extreme humidity or high temperatures, conserving energy becomes critical. Vocalization may decline naturally with metabolic slowdown. Distinguishing thermally driven quiet from predator-driven quiet requires contextual awareness, something canopy residents refine over lifetimes. There is subtle irony in how humans equate noise with vitality. In many ecosystems, abundance is measured by sound richness. Yet in predator-dense forests, silence can represent coordination rather than decline. A canopy that falls quiet is not necessarily empty. It may be collectively attentive. Evolution has shaped howlers to invest in sound strategically, not constantly. Young howlers learn this balance through observation. Juveniles initially vocalize in rough imitation, but gradually synchronize with adult timing. Social learning refines when to call and when to withhold. This cultural transmission within troops enhances group survival. Silence becomes inherited behavior as much as instinct. Ecologically, howlers influence forest structure beyond acoustics. As folivores, they shape leaf consumption patterns, affecting plant regeneration. Their movement spreads seeds across territories, contributing to canopy diversity. When alarm economy alters their spatial use, reducing travel during perceived threat, seed dispersal patterns shift accordingly. Predation risk indirectly shapes plant community composition. As you continue forward beneath a silent canopy, your perception remains grounded in the visible. Without booming calls, you assume reduced occupancy. Yet, the absence of broadcast may indicate heightened awareness. The entire upper layer may be engaged in still observation. Branches that appear static conceal curled tails, anchoring bodies against trunks. Faces partially obscured by leaves track motion without announcing it. What can happen in such moments is rarely dramatic. The troop may simply wait until you pass before resuming normal acoustic exchange. But the ecological lesson is profound. Sound in the Amazon is negotiated. It is not constant output, but calculated expenditure. Howlers regulate this economy with precision, balancing territorial display against predation risk. When they go silent, the forest's architecture shifts subtly. Dominant frequencies disappear, altering how other species perceive space. The canopy-level cascade can dampen broader sound production, creating an impression of vacancy. Yet, beneath that impression lies strategic restraint. Understanding this dynamic reframes silence from void to signal. It is not the absence of life, but the presence of decision. The canopy does not always warn through alarm calls. Sometimes it withholds them. And when you mistake that withholding for emptiness, you move through a forest that is fully aware of you, simply choosing not to broadcast the fact. In that restrained quiet, the jungle demonstrates a sophisticated balance between communication and concealment. Howler monkeys, famous for their thunderous roars, reveal their ecological intelligence most clearly in the moments when they choose not to roar at all. At the river's edge, danger does not begin with a splash. It begins with restraint. The Amazon's margins are usually restless places, dragonflies tracing erratic grids over the surface, fish dimpling the water in quicksilver flashes, capybaras wading knee-deep to graze aquatic grasses, macaws descending in noisy flocks to drink and lift away again in color and chaos. The boundary between forest and river is rarely still. Yet when a large caiman settles into position along that margin, the change arrives not as visible movement, but as subtraction. Ripples diminish. Casual splashes thin out. The bank looks momentarily unclaimed, almost peaceful. This is the first layer of the timing trap. A caiman does not chase water. It occupies geometry. The body aligns parallel to shore, eyes and nostrils just breaching the surface, while the rest remains suspended in buoyant stillness. Dark dorsal armor breaks the waterline like a drifting log, but even that illusion fades when silt clouds soften the outline. Unlike terrestrial predators that must close distance, a caiman waits for distance to collapse naturally. The river does the moving. Animals must approach it. Prey species understand this far better than humans do. Capybaras, deer, peccaries, even large birds synchronize their approach to water in subtle coordination. The riverbank is a resource hub, hydration, mineral intake, cooling, escape corridor, but it is also the narrowest bottleneck in the landscape. To drink, an animal must lower its head and compromise vision. The throat extends. The center of mass shifts forward. In that posture, reaction time shrinks. Over generations, selection has favored individuals who do not approach water randomly. They arrive in waves. You can observe it if you wait long enough. A hesitant pause spreads through a herd before descent. One animal scans, another tests the shallows, a third stamps lightly at the mud. Only when several bodies commit simultaneously does the group lean down. The synchronization dilutes individual risk. A caiman can launch only once per decisive burst. Multiple targets create uncertainty. Timing, not speed, becomes the prey's defense. The caiman's anatomy is built to exploit that narrow vulnerability window. The skull is elongated and reinforced, jaw muscles anchored for rapid closure with immense force. Sensory organs called integumentary sensory organs, small pressure receptors embedded along the jawline, detect minute disturbances in water. A single ripple from a hoof or muzzle transmits through the surface tension and registers across that network. Vision above water remains steady, but much of the hunting information arrives as vibration. The predator does not need to see the entire animal. It reads displacement. Thermoregulation shapes this ambush geometry. Caimans are ectothermic, relying on environmental heat to regulate internal temperature. During cooler hours, they bask along banks to raise metabolic readiness. As body temperature climbs, muscle contraction speed improves, digestion accelerates, and reaction time sharpens. By late afternoon or early evening, when many mammals descend to drink after a day of feeding, the caiman's physiology is primed. The river appears calm precisely when the predator is most prepared. The illusion of calm is reinforced by silt. Amazonian rivers often carry suspended sediment that dulls underwater visibility. Beneath the opaque surface, The caiman's body can remain motionless with minimal fin adjustments. The tail, laterally flattened, is both rudder and engine. When the strike comes, propulsion is delivered in a single lateral sweep, generating explosive forward acceleration over a short distance. There is no prolonged pursuit. The attack is vertical and upward, designed to breach into the drinking space in a fraction of a second. Prey behavior reflects awareness of this geometry. Capybaras often drink from slightly elevated banks, where the slope reduces immediate submersion risk. Deer may favor narrower tributaries with clearer visibility. Birds approach in quick succession, dipping and lifting rapidly rather than lingering. Even fish alter surface behavior when large crocodilians are present, reducing erratic splashing that might attract secondary predators. The entire waterline becomes a negotiated schedule. When you arrive at that riverbank, you do not perceive the schedule. You see still water and interpret safety. From a human perspective, turbulence reads as danger and calm reads as reassurance. But in predator-shaped systems, turbulence can mean randomness, fish movement, current shift, wind. Stillness can mean alignment. The caiman's ambush geometry is fully assembled when the surface looks undisturbed. Leaning forward to wash your hands shifts your balance in the same way it does for prey. Your center of gravity tilts toward the water. Your arms extend, reducing stability. The angle of your neck exposes the carotid region. To a caiman, the silhouette above water becomes another forward-leaning shape at the precise vulnerability window evolution has exploited for millions of years. Most encounters do not escalate. Caimans rarely target large, unfamiliar mammals without provocation. But the structural similarity remains biologically significant. The timing trap extends beyond single ambush events. Chronic crocodilian presence alters migration patterns and habitat use along river corridors. Herbivores may prefer open banks during certain seasons, even if forage quality is lower. Nesting birds adjust colony placement to avoid high-density caiman territories. Fish species shift spawning grounds in response to predator density. The river's edge is not just a drinking site, it is a dynamic interface shaped by predation pressure. Interestingly, caimans themselves are constrained by timing. Extended stillness conserves energy but limits oxygen intake. Although capable of long submersion, they must periodically surface fully to ventilate. Their ectothermic metabolism means activity levels are temperature dependent. Too cool and reaction speed drops. Too hot and prolonged exertion risks metabolic stress. The predator must select ambush windows carefully, balancing physiological readiness against opportunity. There is also competition. In regions where large anacondas or giant otters share waterways, caimans adjust territory and timing to reduce direct conflict. Juveniles face predation from larger crocodilians and even from jaguars along banks. The waterline is not solely their domain, it is contested ground. Yet adult black caimans, among the largest predators in the Amazon basin, command substantial influence over these margins. Their presence alone reshapes daily rhythms. The absence you notice, fewer ripples, fewer drinkers, is a behavioral echo. Animals are waiting for the same safe second. That second often arrives when enough individuals gather to dilute risk or when shifting light conditions reduce silhouette clarity. Prey do not eliminate danger, they distribute it. The riverbank becomes a pulse system. Approach, drink, retreat, pause. Approach again. From an ecological perspective, this choreography stabilizes the system. Predators remove vulnerable or inattentive individuals, maintaining population health. Prey vigilance maintains predator efficiency by filtering out high-risk engagements. Over evolutionary time, both sides refine timing. The caiman's patience is not laziness, it is adaptation. Energy invested in stillness pays dividends when the geometry collapses correctly. If you stand long enough and observe carefully, you begin to read the river differently. Calm water at a busy bank can be suspicious. A sudden cluster of animals descending together signals coordinated risk-taking. A log that maintains identical position against subtle current shifts may deserve a second look. The waterline becomes less about reflection and more about pattern. The trap is not the strike alone. It is the misinterpretation of quiet. The river's smooth surface can represent equilibrium achieved through tension rather than safety achieved through absence. By the time the geometry is visible, the upward surge, the explosion of silt, the violent break in symmetry, the decisive moment has already passed. Caimans do not need constant motion to dominate their environment. They govern through timing. They allow the river to draw life toward them and then select the precise second when vulnerability peaks. In that sense, the waterline is less a boundary than a clock face, its hands moving through light, temperature, and collective behavior. When you lean toward that calm surface, you are stepping into a schedule written by predation. Most days, nothing happens. The system holds. But the stillness you interpret as harmless may, in ecological terms, be the exact condition required for ambush geometry to function perfectly. The water does not warn. It reflects. And beneath that reflection, timing waits. There are moments in the Amazon when the forest feels suspended. Birdsong thins. Frogs fall silent. Even the distant splash of larger animals at the riverbank disappears into a humid stillness. You might interpret this as safety, assuming that if nothing large is moving, nothing is hunting. But silence in a rainforest does not eliminate signals. It redistributes them. And in that redistribution, one of the smallest predators in the ecosystem becomes dominant. Mosquitoes do not hunt with sound. They do not need the rustle of leaves or the rhythm of footfall to locate a host. Their sensory world is built around chemistry and heat. While larger predators track vibration, silhouette, or movement corridors, female mosquitoes operate within invisible plumes, currents of carbon dioxide, lactic acid, ammonia, and volatile organic compounds that leak continuously from warm-blooded bodies. In a still forest, these plumes become clearer. Every breath you exhale carries carbon dioxide at concentrations far higher than ambient air. Insects within the family Culicidae possess specialized receptors on their maxillary palps capable of detecting even minute increases in CO2 from considerable distances. When atmospheric pressure shifts ahead of storms, or when wind stalls in heavy humidity, air currents slow and stratify. Scent plumes do not disperse quickly. They linger, forming chemical trails that stretch through understory layers like translucent ribbons. In such conditions, you are not a moving object. You are a lighthouse of chemistry. Mosquitoes are exquisitely tuned to layered detection. Carbon dioxide alerts them to potential hosts at range. As they close distance, thermal sensors guide them toward warmer surfaces, distinguishing living skin from cooler bark or stone. At closer proximity, chemical cues refine targeting. The composition of human sweat, particularly lactic acid concentration and skin microbiota byproducts, varies between individuals, influencing attraction levels. Some people emit scent signatures more appealing than others, a reality shaped by both genetics and microbial communities. In a forest that has grown quiet for other reasons, perhaps atmospheric recalibration or predator-induced stillness, you may believe you have regained stealth. But mosquitoes are indifferent to acoustic reduction. If anything, the stillness enhances their efficiency. Larger animals holding position generate fewer disruptive air currents. Bird wings do not slice through humidity. Mammals are not trampling leaf litter. The air becomes a stable medium in which chemical gradients persist longer. After pressure shifts, convection patterns alter. Warmer ground layers may trap humid air close to the surface. Your exhaled breath, heavy with moisture and CO2, drifts slowly rather than dispersing upward. Mosquitoes intercept these gradients and adjust flight accordingly. Their flight path is not random. It is guided by concentration differentials, ascending or descending until signal intensity peaks. Unlike many predators in the rainforest, mosquitoes rely on collective abundance rather than individual power. A single bite may be trivial, but dozens create distraction, irritation, and physiological response. The female mosquito requires blood primarily for egg development. Proteins and iron extracted from hemoglobin support oogenesis. Males, in contrast, feed on nectar and do not bite. This division of labor underscores the reproductive imperative behind what feels like nuisance behavior. Ecologically, mosquitoes occupy a dual role. They are predators at the microscale and prey at the macroscale. Dragonflies, bats, fish, and even other insects consume them in vast numbers. Their larvae develop in standing water, puddles, bromeliad reservoirs, river margins, filtering organic debris and contributing to nutrient cycling. Yet their feeding behavior intersects directly with disease ecology. In many tropical systems, mosquitoes serve as vectors for parasites and viruses, transmitting pathogens between hosts. When the forest quiets and you stand exposed, sweating under rising humidity, your physiology amplifies their attraction. Stress increases respiration rate. Faster breathing elevates CO2 output. Anxiety-induced perspiration alters skin chemistry, potentially increasing lactic acid emission. Your attempts to remain alert for larger threats inadvertently enhance chemical broadcast. As mosquitoes converge, your reaction changes the acoustic field. Slapping skin produces sharp, irregular impacts. Fabric rustles. You shift weight frequently, breaking the stillness that once cloaked you. In striving to remove the smallest predators, you generate signals detectable by larger ones. The irony is evolutionary. The irritation response evolved as defense against blood loss and infection, yet in certain contexts it compromises stealth. Mosquito feeding mechanics reveal a precision that belies their fragility. The proboscis is not a single needle, but a bundle of specialized mouthparts enclosed in a flexible sheath. Two maxillae soar gently into skin, while a labrum searches for blood vessels. Saliva injected during feeding contains anticoagulants and anesthetics, minimizing immediate detection. The immune system responds moments later, producing swelling and itch. The bite itself is a biochemical negotiation between parasite and host. In still air, the negotiation favors the insect. Humidity influences flight endurance and survival. Mosquitoes lose water rapidly in dry conditions. High humidity prolongs viability and feeding window. Pressure drops preceding storms often coincide with rising humidity, creating optimal microclimates for host-seeking activity. While frogs may fall silent to conserve energy or avoid wasted calls, mosquitoes may intensify movement in the same interval. The forest's quiet becomes deceptive. Larger animals conserve motion, but the smallest predators exploit the chemical clarity that follows. Even thermoregulation plays a role. Warm skin surfaces radiate infrared energy detectable at close range. After physical exertion, peripheral blood vessels dilate to release heat, increasing surface warmth and enhancing detectability. In your effort to move quickly through silence, you become warmer and more chemically conspicuous. From an ecological perspective, mosquitoes illustrate how predator-prey dynamics operate on multiple scales simultaneously. While you scan for jaguars or caimans, micropredators assess you chemically. Both processes unfold within the same landscape, governed by different sensory hierarchies. Silence may suppress acoustic signals, but it cannot mute respiration or metabolism. What can happen in such moments is rarely dramatic in cinematic terms. You may not face immediate danger from large fauna. Instead, you lose concentration. Repeated bites fracture attention. Slapping interrupts careful footing. A misstep on wet roots becomes more likely. The cascade begins not from visible threat, but from biochemical attraction. Yet mosquitoes themselves are not malicious actors in this system. They respond to cues honed by millions of years of evolution. Their larvae transform stagnant water into future wings, linking aquatic and terrestrial ecosystems. They pollinate certain plants when feeding on nectar. Their existence supports entire food webs. The discomfort they cause is an incidental byproduct of reproductive necessity. Understanding this reframes the stillness. Quiet does not mean absence of life. It may indicate redistribution towards sensory channels invisible to human bias. The Amazon never truly powers down. It shifts modalities. When acoustic intensity drops, chemical signaling may dominate. When visible movement slows, microscopic interactions accelerate. If you stand calmly and regulate breathing, reducing sudden movements, the chemical plume remains, but the acoustic disruption lessens. Covering skin and managing sweat can diminish attraction. Awareness replaces panic. In this adjustment, you reclaim some control over the interaction. The deeper lesson is ecological humility. In predator-rich environments, threat is often imagined as large and visible, but vulnerability frequently arises from overlooked scales. A quiet forest can harbor intense biochemical activity. Mosquitoes, nearly weightless and almost silent, exploit the physics of still air more effectively than many larger hunters. As the humidity thickens and the canopy remains subdued, you recognize that you are not alone in the silence. You are broadcasting through breath and heat. The jungle listens in multiple frequencies at once. Quiet does not mean safe. It means the dominant signal has changed. In Amazonian blackwater, vision is often the least reliable sense. The water is stained the color of steeped tea, tannins leached from decaying leaves turning entire floodplains into dark mirrors. Silt drifts in suspended sheets, diffusing light into a dim bronze haze. In these conditions, you do not see coils first. You see physics. A meniscus trembles along the edge of a floating leaf. A reed angles slightly against the prevailing current. A wake forms that is too smooth, too deliberate, as though the water has chosen a direction without wind to justify it. The snake itself remains absent from view, but the surface is speaking. The green anaconda moves through this environment as mass disguised as drift. Unlike crocodilians that breach upward in explosive bursts, anacondas often advance as a submerged pressure system. The body is thick, muscular, and neutrally buoyant when lungs are partially inflated. By modulating air volume, the snake can adjust how much of its dorsal surface approaches the interface between water and air. Only the eyes and nostrils may break through, aligned along the top of the skull to allow forward scanning, while the rest of the body remains concealed. Yet even when no anatomy is visible, the water reveals displacement. Fluid mechanics govern this revelation. Any object moving through water generates microwaves and pressure gradients that propagate outward faster than the object itself. In still conditions, these gradients are subtle but measurable. Prey species that frequent flooded forests, capybaras, wading birds, even fish, are attuned to these shifts. A surface tension line that bends where it should remain straight can indicate submerged mass. A floating fragment of vegetation that rotates without obvious eddy suggests displacement from below. These are not dramatic splashes, they are deviations from expectation. Speculation grounded in sensory ecology suggests that many prey animals detect pressure displacement in ways analogous to how humans sense someone approaching from behind. Water carries information efficiently. Fish rely on lateral lines, arrays of mechanoreceptors along their flanks, to detect minute vibrations and flow changes. While mammals lack lateral lines, they possess acute tactile sensitivity in limbs and vibrissae. Capybaras, standing knee-deep, may register low-frequency shifts against their legs. Wading birds feel ripples transmitted through their tarsal bones. The perception is not visual confirmation, it is unease generated by altered physics. The anaconda's physiology supports this stealth. As a large ectothermic reptile, it conserves energy through stillness. Its metabolism allows prolonged periods of inactivity punctuated by decisive action. Muscle fibers arranged for sustained constriction enable powerful but economical movement in water. The snake does not need to rush. It allows the environment to deliver prey into range. In flooded forests during the wet season, when vast tracts of land lie submerged, prey species navigate by memory and elevation cues. Channels between trees become aquatic corridors. The anaconda occupies these corridors as a moving topography. Thermoregulation influences positioning. Anacondas bask along banks or in shallow sunlit water to raise body temperature, increasing muscular efficiency. Warmer muscle contracts more rapidly, enabling stronger constriction once prey is secured. In cooler blackwater, the snake may move less frequently, relying on ambush rather than pursuit. The interplay between temperature and movement creates predictable hunting windows that prey species attempt to anticipate. Yet even anticipation cannot negate the ambiguity of surface signals. When you step into such water, your own movement generates turbulence that masks subtle cues. Each footfall clouds silt and disrupts microwaves that might otherwise reveal hidden mass. You interpret the lack of visible form as safety. The disturbance you create becomes the dominant signal, overwhelming quieter anomalies. This is the misreading at the heart of the surface tell. Silence and slow disturbance are interpreted as nothing, when in fact they represent restraint. As you wade deeper, buoyancy changes your balance. Water reduces friction against your legs, diminishing lateral stability. Reaction speed slows. The substrate beneath your feet may be uneven, roots concealed under mud. In contrast, The anaconda's advantage increases with depth. Water supports its weight, allowing rapid lateral acceleration without the burden of terrestrial gravity. The snake's body can anchor against submerged branches, converting flexible muscle into a lever system. What feels like neutral ground to you is a three-dimensional advantage to the predator. Anacondas do not rely on venom. Their predation strategy centers on constriction combined with precise bite placement. When striking in water, they often seize prey at the head or upper torso, immediately looping coils to prevent escape. Contrary to older myths of bone-crushing force, constriction primarily impedes circulation and respiration, inducing rapid loss of consciousness. In aquatic settings, drowning can compound this process. The efficiency lies not in spectacle, but in biomechanics. Prey animals respond to these risks with cautious choreography. Capybaras often enter water in groups, scanning for irregular drift before committing fully. Deer that must cross flooded channels move in tight succession, minimizing time spent stationary. Wading birds probe substrate quickly and relocate often, avoiding prolonged stillness that could align them with submerged mass. Even caimans occasionally yield territory to large anacondas, recognizing the constrictor's ability to exploit shallow margins. Seasonal flood pulses intensify these interactions. During peak inundation, when forests become labyrinths of submerged trunks, prey density concentrates along slightly elevated ridges or at the edges of receding waters. Anacondas follow these concentrations, adjusting movement corridors accordingly. Migration patterns of fish and amphibians during breeding seasons create additional feeding opportunities. The snake's ecological role is intertwined with hydrology. Its distribution expands and contracts with the river's breathing. Surface tells often precede encounters by minutes rather than seconds. A reed shifting against current might indicate a slow lateral glide beneath. A wake too smooth may reveal a body displacing water evenly along a submerged axis. Unlike wind-generated ripples that fragment and overlap, predator-generated wakes can appear linear and coherent. Learning to distinguish these patterns requires prolonged observation, not instinct alone. In many cases, nothing happens. The anaconda may redirect away from large, unfamiliar disturbances. Large adults are formidable but cautious. Energy conservation governs decision-making. Yet, the structural vulnerability remains. By stepping deeper into water where visibility is low and footing uncertain, you shift the encounter geometry in the snake's favor. Mobility decreases for you while three-dimensional maneuverability increases for it. There is irony in how subtle the first signals are. Humans often scan for dramatic cues, thrashing, overt movement, visible coils. But in blackwater systems, drama arrives last. The ecosystem communicates through tension lines and pressure gradients long before form emerges. Prey species that survive do so because they treat minor deviations seriously. Evolution has favored sensitivity to almost nothing. Anacondas occupy a complex ecological niche. As apex constrictors, they regulate populations of medium-sized mammals and birds, influencing vegetation indirectly by controlling herbivory. They also serve as prey when young, vulnerable to caimans and large birds of prey. This dual role reinforces the importance of early detection on all sides. Even the snake must read surface tells to avoid larger threats. Standing knee-deep in dark water, you begin to understand that the river does not conceal. It translates. It translates mass into ripple, movement into meniscus shift, intention into wake. The absence of visible coils does not indicate absence of presence. It indicates that presence is operating within physics rather than spectacle. The first sign of an anaconda is rarely the body. It is the water behaving slightly differently than expected. A surface line bending without wind, a floating leaf rotating without eddy, a corridor of silt that seems too organized. These are the early chapters of the encounter, written in fluid mechanics. If you misread them and step deeper, you reduce your own leverage while expanding the predator's domain. Most of the time, the system holds and nothing escalates. But the lesson persists. In blackwater and silt, survival depends on reading physics before form. The snake reveals itself through displacement long before it reveals its scales.